So, met z'n Nee, professor. Kijk. Is hij nog eens in de hangouts?
Ik denk dat...
Ik ben bezig. Heb je hem nodig?
Nee, maar ja, David Blackman ging normaal
Ja.
volgen, maar
Ik ga hem nog eens
ik had hem
doorsturen.
oorspronkelijk
Laat hem
gestuurd
laten
van
weten.
12:30, maar...
Het zal wel vroeger zijn.
Ja, oké.
Maar hij zal het wel laten weten, hè? Hij heeft nog steeds.
Zal hem
Om zijn...
berichtje sturen.
Hoe laat is het dan nog? Is het ochtend of is het avond? Is het
Nou
nu
ja,
zo?
nee, het is in het tweede, dus
Ah,
het is
oké,
daar
zo.
's ochtends.
Nee, is geen probleem.
Are you ready? Ja.
Altijd rustig blijven.
Ik ga nu heel doorstellen.
Ja.
Kijk jij even of het interessant zou kunnen zijn.
Is also coming from it? Yeah, he's there. So some things never change.
We are waiting for.
Yeah.
Okay, so shall we start? Okay, so we will have 15 to 20 minutes for presentation.
Okay.
Okay, then the academic committee will make a question about your work and about your presentation.
Yeah.
And after that, we will ask you to leave the room to evaluate the candidate.
Yeah.
Okay. So whatever you want, you can start.
Hello everyone. My master's thesis topic is sensitivity analysis in formal race car dynamics. And so before we start sensitivity analysis, I would like to show you some views of the car which I worked on. It's an E-Motorsports Cologne car. This is the front view, and all these views will show you the different race car parameters that are used in this sensitivity analysis. So here you can see in the front view the tire camber, front 0.8 degrees and rear 0.6 degrees. And the suspension used in this car is push rod suspension. The side view you can see the wing characteristics like front wing, diffuser used in aerodynamics, and the rear wing. The aerodynamics characteristics are CLA, which means downforce coefficient multiplied by frontal wing area of the wing, which is 3.8. CDA is related to drag, so drag coefficient multiplied by frontal area of the wing, and it is 1.7. Coefficient. Center of gravity is 390 meter of this car, and the tires are used from the vendor called Bussier, and the tire radius is 192 millimeter with 20 psi pressure and temperature 293 Kelvin. So the third view is the top view, and on the right hand side you can see the battery box with battery configuration 144 in series and 4 in parallel combination with total capacity 6.47 kilowatt hour, and the battery weight is 60 kg. The tow-in angle used for this car is 1 degree front and 1.5 degree rear. The anti-roll bars, which are in yellow color, you can see here, they are torsion anti-roll bar, and the anti-roll bar rate used here is 478.2 Newton millimeter front and 275.5 Newton per millimeter rear. And on the left hand side is a double wishbone suspension in red color, and they are made of CFRP tubes with glued aluminum rod, and the spring damper system colored in green. The vendor used for this spring damper is Tolin's ETX25 FSAE, and the spring rate is 70 Newton per millimeter, and the damper FSAE, and the spring rate is 70 Newton per millimeter, and the damper characteristics are further explained in the damper section. So, in this sensitive analysis, lap time simulation is used. So, what is lap time simulation? It's a kind of software where a race engineer can input all the parameters from tires, aerodynamics, then motion ratios, anti-roll bar rates, suspension, everything inside. And when we run the simulation, a virtual simulation is obtained. And based on that virtual simulation, we can make design concepts of the car, like the actual car. So this is about lap time simulation. And there are different softwares available in the market, like chassis sim, lap sim, car sim. And I personally met with lap sim and car sim people in whether it's a Hanover trade fair or Bus World in Brussels. And I asked personally them which software will be perfect for me in order to do the lap time simulation. And they told me car sim and lap sim need bunch amount of data or extensive amount of data to run the simulation, and chassis sim is for the basic simplistic software where I can run simulation with limited amount of data, and that's why I choose chassis sim for this lap time simulation. So what are the assumptions in sensitivity analysis? So the main assumption is when the car runs in chassis sim, it uses the center line of the track. So it is not possible to know from the virtual simulation whether the car is understeering or oversteering. So this information is not cannot be seen in a chassis sim. The second thing is the moments, like whether it's roll, pitch, or your moments. This cannot be judged or cannot be seen with the help of chassis sim. So I cannot say whether the car is rolling at this angle or the car has some heave motion in braking or in acceleration. So these results cannot be seen from this chassis sim. And the best results for comparison in sensitivity analysis from this chassis sim are speed, throttle position, and the lap time achieved on a specific track. The aim of this sensitivity analysis is to obtain the best parameters with which the lap time is achieved. So whether it's spring rate or the damper rate, which is the best race car parameter with which this lap time is achieved. So that is the aim of this. So which are the factors I used in sensitivity analysis? The suspension geometry and battery specifications are kept constant, and the parameters on which this virtual simulation is run in this sensitivity analysis are spring rate, damper characteristics, anti-roll bar rate, motion ratios, tire characteristics like camber and toe angle, and the last one is downforce and drag coefficients in aerodynamics. The track used here is FSAE sample track with 690 meter of track length. And when we run a simulation with the default characteristics I chose from the e-motorsports Cologne car with everyone, with default characteristics, the lap time achieved is 38.742 seconds. And what is meant by sensitivity analysis? Sensitivity analysis is like making plus minus 10% changes to all these race parameters. For example, if I choose a spring rate of 70 Newton per millimeter, then in sensitivity analysis, I make plus 10% to spring rate and minus 10% to spring rate and run the simulation based on plus minus changes and to know whether the lap time is improved or not. The first one is suspension geometry. As all we know, suspension is a really important part in any race car because in suspension geometry, the important parts are spring damper system and the suspension frame. suspension frame actually connects unsprung mass, and the sprung mass means the chassis with a suspension frame. And the main aim of suspension geometry is to absorb the vibrations of uneven tracks on the road, um, or the load transfer or the weight transfers during speeding, during braking, or during cornering. So to absorb these changes and give a comfortable ride. So that's the main purpose of suspension. As you can see, this is the rear view of E Motorsports Cologne car, and the suspension used here is wishbone suspension. This is the unsprung mass, and this is the chassis or the sprung mass, you can say. This is the motion. The pronunciation used here is jounce. Jounce in the sense when the car goes over a bump and the spring compresses, it is called jounce movement, the upward movement. And the second is rebound movement when the car goes in a dip. The downward motion or the extension of spring is called rebound movement. And so there are different parameters in suspension geometry. The first one is suspension pickup points. These are the points where unsprung mass and sprung mass are connected. So these are the suspension pickup points. Second is roll center migration. When we design a suspension, this criteria is really important because roll center is a point when you can see from the front view. When the suspension frame connects to a point here, and when we join this point from the point of contact of the tire with the track here, and same from the right side tire, this external center, and the point at which the tire is connected, it is connected to this point, and when these two lines meet each other, is the roll center. And it's important because the height of roll center from center of gravity is really important because it actually tells you how much the car rolls. This height gives you actual the rolling moment of the car on the track. So higher the height, higher will be the moment, and that's why this roll center migration is really important while designing a suspension. Second one is camber variation. When we all know when the car runs in dynamic events, the due to the bump or due to cornering, load transfer happens, and this actually change the camber angle of the car, because when the car goes like this, the right hand tire will be lean and its camber angle changes. So based on some analysis or from the test, we know how much this camber angle changes, and if we know the variations in camber angle, accordingly we can design the suspension. Anti-squat and anti-dive is the pitching criteria or the pitching characteristics of the car. When the car brakes, it leans forward and the load transfer happens in the front, and when it accelerates, the load transfer happens on the back of the car. So this pitching moment is actually called the anti-squat and anti-dive, and as you can see from the side view, when the suspension frame meets at this point and the tire's contact point meets to this at this point, this is the center line passing through the center of gravity, and the line at which it touches to the center line, it's called from the front is called anti-dive because it's during braking, and from rear because when the acceleration happens, the car leans backwards, and from the rear it is called, from this point you can see, anti-squat. So the anti-squat point goes through the center of gravity. It means all the load during acceleration is transferred to the suspension frame, and it do not transfer to the spring, and it actually helps the lifespan of spring. But when you see in front, this point meets at the 50% of as compared to the height of center of gravity. It means the 50% load is passed through the spring, and it means the lifespan of spring can be hampered with this. So the main criteria during suspension design is this anti-squat and anti-dive point should pass through the center of gravity so that most of the load will pass through the suspension frame. So that's why these properties are really. These are the suspension geometries, the suspension points at which the frame is connected to the P Motorsports Cologne car. So this is the front suspension points, and these are the rear suspension points. Yeah, the first part in sensitivity analysis is spring rate, because suspension characteristics are kept constant. And as you know, spring absorb the vibrations from the tracks, and it gives the comfortable ride on the track. So these are the springs highlighted in green color. This is the front springs and rear springs. So what are the main importance of springs? It depends, like when the car runs on the track and driver feels that the car is understeering. Understeering happens when the front tires lose contact with the track. So it's important the front tires should not lose contact. So that's why the front spring rate is reduced, and as the front spring rate is reduced, the soft spring in the front absorb all the load variations during cornering, and the understeering can be avoided. And same with oversteering. Oversteering happens when the rear wheels of the car lose contact with the track, and so for this reason, to avoid an oversteering, the rear spring of the car or the spring rate at the rear is reduced. So all the weight transfer is absorbed by the rear springs, and oversteering can be reduced. These are the simulation results based on spring rate. Uh, yeah, for the sensitivity analysis, we all know that the spring rate default is 70 Newton per millimeter. So minus 10% is 63 Newton per millimeter, and plus 10% is 77 Newton per millimeter. So virtual simulation is run based on these two values, keeping all the other parameters constant. And the simulation results based on this spring rate are shown below. The blue line spring and the red line corresponds to hard spring. Soft spring in the sense spring rate with 63 Newton per millimeter, and the red line corresponds to 77 Newton per millimeter. And you can see the higher speed peaks are achieved with soft spring through this blue line. This is the speed kilometers per hour, and this is the throttle position. So higher speed peaks are achieved with soft spring, and again the throttle positions, they are achieved 100%, you can see here, with the soft spring. And hard spring, in case of hard spring, the throttles cannot completely achieved to the 100%. These are the lap times. With default spring is 38.642, for soft spring is 36.742, and for hard spring is 38.622. And from this, you can see approximately 2 seconds are saved with respect to soft springs compared to default and hard springs. And these are kind of section-wise timings for soft and hard springs, like turn 1, straight, again turn straight, and turn 3. So the blue line represents the fastest timings. So with soft spring, it's almost fastest in all the turns and straights. The second part is damper characteristics. Dampers are connected with springs. So when the oscillations or the vibrations from the track are absorbed by spring, these are damped with respect to damper. Without damper, spring will not be efficient. So this is actually a kind of mechanical system of spring damper system. 2% of damping is also available with the tires, but it is neglected in this analysis.
You can present it for 17 minutes, so you should speed up because
Okay.
you have 5 more minutes
Yeah.
for your presentation.
Okay. So for the damper characteristics, in sensitivity analysis, so these are the damper characteristics which are chosen default, and 10 plus minus 10% changes are made with the damping force. So the damping velocity is kept constant, and the damping force in bump and in rebound is made changes with plus minus 10%. And based on that, a simulation is run. Steep damper is plus 10% changes to the damping force, and soft damper is minus 10% to the damping force. So you can see the higher peaks are achieved with steep damper, and soft damper is the speed responses, or the when the car brakes starting the turn, they are not good, and when the car goes out of the turn, the the speed variations are quite good with the steep dampers. So the conclusion of this sensitivity analysis with damper characteristics is steep damper has good lap time compared to the soft damper. Next part is anti-roll bar. The main purpose of anti-roll bar in race car is to prevent the roll when the car goes in the corner. Rolling happens because of the weight transfer, and their purpose is to minimize this roll. As we know, the default anti-roll bar rate is 478.2 Newton per millimeter for front and 275.5 Newton per millimeter for rear. And the values used for this analysis are 430.38 for minus 10%, and 526.2 for plus 10%, and same for the rear. And from this graph, they also seen that blue line for the default, and red for lower anti-roll bar rate, and green for higher anti-roll bar rate. And as you can see, the default value chosen for this anti-roll bar rate, they have higher speeds and higher throttle positions. From the blue line, you can see. And these are the lap times for different anti-roll bar rates. Default is 36.582, and for lower, higher, or the combination of soft and stiff, and stiff and soft anti-roll bar rates, these are higher. So conclusion is the same. The default characteristics chosen for this anti-roll bar rate, they are best or ideal, or the chosen characteristics are best. Next is motion ratio. Motion ratio is the spring travel to the wheel travel. Motion ratio means, so the main purpose of motion ratio is connected with the suspension system, and for race cars, this motion ratio is kept or nearly equal to 1. As you can see, there are 3 motion ratios: 1:1, 0.75:1, and 0.5:1. They are compared, and you can see here, spring to shock velocity for 1:1 is 50, keeping wheel travels constant. 37.5 is for 0.75, and 25 millimeter per second for 0.5. And it is important because for damper, more the damping velocity, more the dampers behave properly in the car. And that's the reason this motion ratio is kept equal to or nearly equal to 1:1. The motion ratio selected for this FSE car is 1.16, and sensitivity analysis, different motion ratios are used, like 0.8, 0.9, 1.2, and 1.3. And this is the virtual simulation based on motion ratio 1.16, 0.9, and 1.2. And you can see the blue line for 1.16. It has higher speed peaks and the higher throttle positions for most of the track, and lap times achieved with these motion ratios for default is 36.582, and you can see all other motion ratios, they have higher lap times. So the default value chosen for this motion ratio is best.
You have 3 more minutes.
Yeah. So the tire characteristics, tire, as you know, tire have really they are the most important parts in the race because of its characteristics or tractive force to the track, and there are some important factors related to tires like slip angles or camber angles with which the tire behavior of the car can be hampered on the race car. The default value chosen for these tires are 0.8 degree negative camber, toe in 1 degree, and rear tire, the camber chosen is 0.6 and toe in 1.5. And these are the values chosen for the sensitivity analysis, plus minus 10%. And the simulation, you can see the blue line is default, and green is lower camber, and red line is higher camber and toe. And again, you can see the blue line represents higher speed values and higher throttle position. So the default tire characteristic chosen, like the camber and toe angle, is good for the best lifetime achieved. And the aerodynamic characteristics. Aerodynamics has the two terminology which are really important. One is downforce and second is drag. Drag, as you know, drag opposes the velocity of the car and it impacts the lap time. And downforce is important because Formula race car have really high speeds, and they should be the tractive. It should be enough tractive force with the wheel and track in the fast cornering. Otherwise, the car will roll in the corners, and that's why downforce is really important. So the main purpose of aerodynamics is to get the highest downforce and less drag, and that's why the front wing, rear wing, and the body of the car is accordingly designed. So this is the front view of the E-Motors to Scullon car. This is the wing section, the front wing section. This is the rear wing with two flaps and the main wing. This actually the diffuser part. When the air passes from front wing to the rear of the car, this diffuser provides downforce because the air passes from the down has lower velocity compared to the air passing above the or over the body. So according to Bernoulli's equation, the lower part has low pressure and the higher part or the body part has more pressure. So it pushes the car towards the ground, and that's why more downforce is created. And the sensitivity analysis, as I already discussed, these are the default values for aerodynamics, and sensitivity analysis, these two values are considered. And this is the sensitivity analysis for aerodynamic characteristics. Blue line is default, red line is for higher downforce and drag, and green line for lower downforce and drag. And as you can see, higher speeds and throttle positions are achieved with the default aero properties. Yeah, so the conclusion of this sensitivity analysis is base lap time is achieved with soft spring, with spring rate 63 Newton per millimeter and stiff dampers, and keeping all the other properties like aerodynamics, motion ratio, the entire characteristics constant. Yeah, and the base lap time achieved is 36.582 on a track of 690 meter. And the lap time achieved with default characteristics is 38.642. So according with this sensitivity analysis, 2.06 seconds are improved. Yeah. So
Okay, thank you very much for your presentation.
Mhm.
If you agree, I will start with some questions, and then I will give the floor to the members of the tribune. I want to make some comments about how you have presented your master thesis, and I will say that it's key to firstly introduce which are the objectives of your research.
Yeah.
Okay. You should always start making clear which is the objective of your research, which is the key points of your presentations, instead of introducing, let's say, general theory concepts. Okay, you have used more than 60% of your time for theory, and then you have to speed up from just presenting some data. So this is very important, and I want to say that presenting data is not presenting information, and you should try to summarize and to present the conclusions of your research during a presentation, not to explain, not to show raw data as graphs
Mm-hmm.
where the audience has to analyze which is the data, which should be the information extracted from that graph or from that images you are presenting. I want to make some questions regarding the content of the work. And first, I would like to give you a quick explanation on how you have selected the design of experiments.
Uh,
How you have defined your design of experiments. You have presented some parameters to be analyzed
Yeah.
and in some ranges.
Yeah.
How you have defined that design of experiments.
The main purpose of the sensitivity analysis is the suspension geometry. So actually, when I started, the team wanted me to give some design concept based on suspension because they were not sure uh, if the suspension is behaving properly, and that's why the spring rates, damper rates, motion ratios, aerodynamics all are connected with suspension, and that's why I choose these parameters for this analysis.
But my question is more related. It's more related with the range
Mm-hmm.
of that sensitivity analysis. And my second question is linked to this. It's have you evaluated any interaction between variables?
Means how I choose these default parameters, or
You have why you have selected that numbers,
Okay.
that ranges for the parameters,
yeah.
and have you done any interaction analysis between variables?
Okay. These parameters I personally chosen with the respective heads of the team, uh, whether it's aerodynamics head or suspension head. So I personally get all the default parameters from them with the car, and they told me like how aerodynamics like downforce and drag coefficients are achieved with the FE analysis, for example, and that's why I chose them. So my work is to get these parameters and run the simulation. And based on the, you can say the plus minus 10%, for example, you say why I choose that plus minus 10%. It could be plus 20%, minus 20%. But I also made simulation with till plus minus 30%, so that the value chosen should be correct to give best lap time. And
I think it's something missing. It's something missed here.
Mhm.
It's how the spring rate is affecting the damping coefficient or the damping force
Mhm.
or the motion ratio, because
Yeah.
once you are changing one parameter, you are changing the other.
Yeah.
And how a change is making influence in the others should has been analyzed in order to fully understand what are you really doing, because uh, if you change the motion ratio,
Yeah.
you are changing the damper force. So if you're changing the spin rate, you're changing how the damper is behaving.
Um,
So interaction between variables, so I think it's something that should have
No,
been analyzed.
the thing is, motion ratio comes first because when you decide the ride frequency of the car, because you know when the car goes over a bump, it has some vibrations in the front and rear. So based on this ride frequency, you know how much damping you need for the car to damp these vibrations. And once motion ratio is defined, damping, you can define the damping. Once the damping is defined or the damper's characteristics are designed,
Once you change in motion ratio,
motion ratio is not changed at all. I kept constant 1.16.
you've shown results on you've shown an analysis on
Yeah.
on how motion ratio is changed.
Yeah. Yeah. Motion ratio when it changed plus or minus 10%, as you can say. But it with default, as explained, we get the best lap time with default. So it will not affect my conclusion in advance. If with the plus or minus 10% motion ratio, it is affecting the lap time, then you can say, okay, it's hampering other characteristics. But with default, I don't think so.
I will give the floor to the other members of the academic
Okay.
board. Yep.
Okay, so I have just very few comments. First comment is I come back to the first comment of Johan. It's important for us at the beginning of the presentation, at least also to have presentation of objective, but of the context.
Yeah.
Where do you spend your master thesis? What was in place when you arrived? Because you do not create the car by your own. So what was the situation in order for us to understand? We need to understand at the end the huge amount of work that you have done.
Yeah.
But in order to understand this huge amount, we need to understand the starting point, the ending point.
Yeah.
It's important for us. So this is, and also because when you choose your software, for instance, there is some, I think in my point of view, some technical characteristic. You said, okay, it is better than this one and so on. But there is also some political characteristic. Maybe this software is better because I can exchange some data with other software, or maybe because a lot of people in my lab already use this software and so on.
Yeah.
So it is not only technical characteristic. There is also non-functional, what we call non-functional characteristics.
Yeah.
Okay, that you do not mention here. For instance, if the software is in place for 2 years in your lab,
Yeah.
you can justify all what you want from a technical point of view. But in fact, you use this software because it was in place in your lab, and okay, and
No,
because
but,
because maybe people have also some knowledge. I don't know if this was the case. You discover,
I found this software myself.
okay,
Yeah, and that's why I said I contacted with people from other softwares, going personally to the Hanover Mesa or to the Brussels Expo, personally contacting them like which software should I use for this, and
Okay.
based on that I chose this.
and you did not discuss this point with your supervisor of the company or in the university or not?
I already discussed this. point,
Okay.
Yeah.
Yeah, because normally the decision is not made only by you.
No, no, no.
Okay. From just a second question from a technical point of view, it's interesting to simulate, but you have two vision in the simulation. Either you say, okay, I take two parts, for instance, the damper with two damping force.
Yeah.
This one and this one, and the soft is better.
Yeah.
But also another way to simulate is to say, okay, now I'm going to find what would be the best value of this force.
Mhm.
Maybe this is between both.
Yeah.
Okay, or between you said okay the soft one is the best.
Yeah.
But if I have something which is softer than this one,
Yeah.
it will be again better and again better and again. So what is the best value of the force, for instance, and maybe to ask if this is possible to find damp with this value. You understand what I want to say?
Yeah, yeah.
Sometimes it's not binary. It's not I simulate this one and this one.
Yeah.
Okay, this one is better. But
Yeah.
maybe there is also solutions in between or on the market.
That's why I said I run simulation based on plus minus 10%.
Mm.
But in order to validate this, whether this analysis is true or not, I again extend my range of simulations till 30%, so
Mhm.
that the value I chosen is correct and give the best lap time.
Okay, and you find exactly a good component with this value? Or?
Yes.
Okay.
Yeah.
Okay.
I have the same question about first inputs. If they're independent of each other, so basically you assume that they're independent. That if you win 2 seconds changing the damper, and 2 seconds if you change the stiffness somewhere else,
Yeah.
would you get 4 seconds win? Would you gain 4 seconds?
No, no. When I started with spring rate, I found that softer spring gives good lap time. Then I use the softer springs and run the simulation with stiff dampers. So it's a combination of soft springs plus stiff dampers, and combined it gives 2 seconds of lap time saved.
Right. And then my other question is, have you done an analysis of the track? For example, there's one corner where there's always a big loss, and do you know where, like, maybe you need a certain stiffness to have the best corner just in one area of the track, or?
No, the thing is the track I used is the default track available in the software. So in actual, I cannot see how the car is running, and because if the real-time test data is available, then it's possible that you can compare this virtual simulation with real-time data of the actual car, and you can actually compare both of them, whether the car is understeering or oversteering. But
That
it's
was
just a
my-
virtual simulation.
That was my last question. How is the simulated data compared to the real world.
Yeah, that's the future aspect of this thesis. That if you know the real-time test data of the car on the actual track, then it can give you a lot of results from this analysis, like whether the car has good velocity or good speed in the cornering or not, or whether the car is slipping in the corners, or whether it's understeering or oversteering. So with real-time data, you can actually comment on this. But with virtual simulation, as I said, this chassis will not actually tell you whether the car is going out of the track or not. So, yeah.
Okay. Now that we're at the springs,
Mhm.
you said that softer springs are better to reduce the lap time.
Mhm.
Why is that?
So because the thing is, there are softer springs and more softer springs, for example. So I have to decide how much I should reduce the spring rate. So I got 63 Newton per millimeter spring rate has the best lap time, for example. I chose this value with doing my simulations till 30%. And the main reason for soft spring is that they absorb most of the vibrations easily compared to the stiff spring, because stiff spring cannot absorb all the vibrations and car can actually oversteer. And that's the reason, I guess, with soft springs that they give better lap time.
But then the softer the better. You would expect to have very, 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 very soft springs.
If you go more beyond 63 Newton per millimeter, for example, 50 Newton per millimeter, softer springs, then because of more spring vibrations or more spring travel, car might be unresponsive in the corners.
Okay.
And that might be the reason.
Okay.
Anyone?
One question from me, not a technical one. I haven't seen your report,
Okay.
but if I would see your report, your written report, and I would compare it with what I've seen here on the screen,
Yeah.
will I notice big differences between what is written and your presentation?
In my report, you will get the brief idea of everything. And presentation is like the main points, what is the simulation and what is the sensitivity analysis. But everything is similar, exact the same, just it's a brief and it's short description.
Do you have the feeling that you adapted the written text to
Uh,
a presentation?
I changed this presentation in order to finish it in at least 30 minutes. So, but it's the same, but I made it point-wise so that people can understand.
Yeah, just one comment.
Yeah,
Yeah, one of the rules is to avoid
yeah,
lots of text
Yeah.
in a presentation.
yeah.
It gives me a feeling that it was a copy and paste of your textbook.
No, not at all. You can compare.
Okay.
But most of the things I changed.
Not at all is a bit strong.
Okay, thank you very much for your presentation
Thank
and
you.
for answering the questions. And if you give us 5 minutes, we
Yeah.
will do the evaluation.
So I would like to urge the students to leave the room.